Here is a second example of thinking with the physics of the Work-Kinetic Energy Theorem. So what I've drawn is a horizontal, maybe tabletop or something, and here's a box that's sliding along the horizontal tabletop with some initial speed like 10 meters per second towards the right. And I've identified it as the initial piece of data that I have about the motion of this box. And then at some point later in time, and also later in location, that I'll designate the final position to think about the box's motion. The piece of data associated with this other time or place is 2 meters per second for the motion, still headed towards the right. And the box has translated by the time f comes around by 5 meters. And so you can see that delta x is a vector that actually is in the same direction as that motion there. But it's a displacement vector, 5 meters long. And so I put the little absolute value magnitude bars so that I don't need to also list the direction of the vector. So this is just the magnitude of the displacement vector. Yeah, so obviously this object has slowed down. And so there's lots and lots of reasons for the object to have slowed down. It could have been that there's a bunch of air. So there's air resistance that the box meets. Another reason that the box could have slowed down is if the horizontal table here was rough in some sense. Yeah, so it doesn't really matter, but the point is I can say that there is an ultimate change in the kinetic energy. And it's interesting that, this would be the kinetic energy at the final interesting time, or data, or time that you have data for, minus the initial. Whenever you do delta, you take the final value and you subtract the initial value, right? That's what delta always means. What is the value after whatever has happened, and what is the value before whatever happens has happened yet? And you put a minus sign. That delta is always with that minus sign, final and initial in that order. And the idea is this is always the work done by the net force, like this. So I go in and I just want to think about this, right? This is explorations or examples of thinking with the work-energy theorem. So what is the work done by the net force? The way you calculate it, right? So back up a step. I can do this. This is easy. I hope that you agree that it's easy. I know the mass is 10 kilograms. That didn't change. And I know the motions, so I can calculate the difference in the kinetic energy. So I won't do it in front of you, but you can do this. Some number of joules is the change. But this part right here is the hard part, and it's equal to the integral. So in general, it is an integral of the strength of the net force dotted with small parts of the displacement. So I'm going to put, maybe your book puts a little r right there, but these are little bits of x displacement. These are small x displacements. So I'm going to add up a whole bunch of small amounts of work done by the net force is the idea. And this net work, if I'm taking I and F to be these two instants in time, is I and F mark the beginning and the end of the path, how the displacements are going to take me along the path. This is very much an integral way of thinking, and it's a very physicsy way to decide what integral to build. F net, though, the way you think about F net comes from thinking like a physicist and building a free body force diagram. This is always true. F net, the way you think about F net is with a free body force diagram. So let's look at our little box sliding across the ground there. So on the box, this is a 10 kilogram box. Presumably, if this is happening on the Earth, I have an acceleration due to gravity everywhere that has that value 9.8 meters per second squared down, right? So here's my box on horizontal ground. There is definitely a weight force acting on the box. And in this free body force diagram, there is also a normal force acting on the box, or some support force. This is the force on the box by this table or surface. And the weight force is the force on the box due to gravity and the fact that Earth is below us, right? Below means the gravitational acceleration points down. The weight forces point down. So these are up and down forces. And then the other force that's part of, if you watched an earlier video, it's part of the way that the table contacts this box, is so the box is moving towards the right, the box is slowing down, and we're going to blame friction. So I'm going to blame kinetic friction, kinetic or sliding friction, because of the fact that the friction force is acting, but the box is moving. So it's a kinetic friction situation. So, so from me being a physicist and deciding what forces go in this diagram, the free body force diagram, there's no reason to have any other forces. This is the complete free body force diagram. And we're going to say, because this box does neither gain motion upwards nor does it gain motion downwards, this box just plainly went this way and it never gained any motion up or down, that the normal force and the weight force, when I add them together in the net force vector, these things add up to 0. So if the net force is equal to the friction force, right? Net means summation, so I only get to use pluses. So plus N plus W. N and W, they balance each other out. There is no force in the up or down direction. So the net force is only the kinetic friction force. So when I realize this for this particular problem right here, when I go and I think about the work done by the net force, that is exactly the same as just the work done by the kinetic friction force, the only force left over that didn't balance out to 0. So it just turns out that that's how this thing works in this particular problem. And I'll just do this. So it's over a bunch of little micro displacements. All the displacements added together ultimately add up to this 5-meter displacement towards the right. So my model for kinetic friction, if you go and you read about how the book presents a model for kinetic friction is simply modeled this way. The kinetic friction force has a magnitude. So it's only defined in terms of its magnitude, actually. I'll tell you about the direction in just a second, but the magnitude is this coefficient for kinetic friction, mu sub k, and you multiply by the magnitude of the normal force. So the coefficient for kinetic friction is just a number. It doesn't even have units, but in particular it's a scalar. And the scalar times this magnitude is another magnitude. This is the idea. In particular, it is independent of place or motion. So as I move from the initial to the final place, I've got all these places in between. And I have a model for kinetic friction that is independent of place, and it's independent also of the fact that it may have been moving faster earlier and slower later. This is a simple model for friction. Whether or not friction actually works that way is a different issue, but it is a simple model for friction. And the point is, so for all intensive purposes, it's constant. So this model for kinetic friction, so I can make an update to this, that this vector that sits here in front of the little dot product symbol is a constant. So it can come out of the integral. So I can even take the dot outside of the integral. The truth is this is the only way that it makes sense. The dot must come out, actually. If you think about the fact that this is a summation, you'll realize why. Because the dot product is distributive is the answer. Like, you could chase that down if you want. But I'm going to integrate up all the small displacements that will take me from the starting point to the finishing point. And what this is the kinetic friction force dotted with the entire displacement. Because this integral from start to finish of all of the small steps in between just adds up to the one big 5-meter step to the side. Yeah. And yeah, so you saw me do some work with a free body force diagram, thinking about the fact that this is the definition of the work done by the net force. It is an integral. If the model of your force is such that it's constant with respect to how the integral is happening, then it is a constant of the integration and can come out as a common factor on the sum. So here it is as a common dot product factor on the sum of infinitesimally length displacement vectors. And out pops this conclusion here.